Understanding the concepts of tidal volume, minute ventilation, frequency, and dead space ventilation is crucial for your professional practice in mechanical ventilation. Tidal volume, expressed in milliliters, is the volume of gas that moves in and out of the lungs with each breath. By default, the T1 calculates tidal volume by multiplying the ideal body weight by 6 milliliters per kilogram. Minute ventilation, often called minute volume, expressed in liters, equals tidal volume times the ventilation frequency, or breaths per minute. The average minute ventilation range in adults is between 5 and 8 liters per minute. Tidal volume and frequency influence minute ventilation and have an inverse relationship. As the ventilation frequency increases, the tidal volume decreases. As the tidal volume increases, the ventilation frequency decreases to allow adequate time for exhalation, a passive process. A helpful rule is that the volume of gas that goes into the lungs should equal the volume of gas that exits. When gas does not exit the lungs as it should, it is called breath stacking. Over time, the trapped air may cause pulmonary hyperinflation, which causes ventilator-induced lung trauma, patient discomfort, and significant challenges to patient safety and mechanical ventilation efficacy. Adjustments to the tidal volume, minute ventilation, frequency, and other controls individualize the ventilation strategy to the patient's pathophysiology. Ventilation dead space refers to the volume of air per minute that does not take part in gas exchange. Ventilation dead space hides in the ventilator circuit, connected equipment, upper airways, and any non-perfused alveoli where gas is present but the blood supply is inadequate. Depending on who you ask, dead space volume equals about 100 to 150 milliliters of gas that does not interact with the alveoli with each breath. This learning module covers the breath cycle, inspiratory time, and the inspiratory to expiratory ratio. It also includes an introduction to the flow waveform to illustrate the lessons. In mechanical ventilation, flow, measured in liters per minute, refers to the rate at which the ventilator delivers a volume of gas to a patient during the inspiratory phase of the breathing cycle. Flow and its corresponding parameters ensure proper gas exchange, lung protection, ventilator synchrony, and patient safety and comfort. The flow waveform provides valuable information about the patient's status on the ventilator. Here is a typical flow waveform that I captured from the T1. The vertical axis represents gas flow in liters per minute, and the horizontal axis represents time in seconds. The solid white line in the middle correlates to zero flow. The portions of the flow waveform above the no flow line represent inspiration and expiration below it. I will dive deeper into specific flow waveforms in an upcoming module. In this module, it is crucial to understand the flow waveform, its relationship to frequency, inspiratory time, and the inspiratory to expiratory ratio. Here is our patient just in case. He requires intubation for airway protection, and fortunately, we have a mechanical ventilator that will provide feedback on his ventilation status. Checking the ventilator control settings, Justin has a frequency of 15 breaths per minute and an I time of 1.35 seconds, yielding an inspiratory to expiratory ratio of 1 to 2. And just in case you were wondering, Justin has a smidge over 2.5 seconds to exhale about 400 milliliters passively during each breath cycle. Let's review and examine how to interpret the settings shown on the flow waveform. The vertical axis indicates flow measured in liters per minute, and the horizontal axis depicts time in seconds. The middle line in the graph labeled 0 separates inspiration from exhalation and is the no flow line. At the end of exhalation, the flow waveform should return to the no flow zone until the patient or ventilator triggers the next breath. More on this topic in a future lesson. The breath cycle begins with the start of inspiration and concludes with the end of exhalation. Here, above the line, is Justin's breath in. As the waveform moves below the no-flow line, passive exhalation ensues. Remember, the inspiratory to expiratory ratio is 1:2. The ventilator delivers a breath over 1.35 seconds. Justin has twice the duration to exhale. The frequency, inspiratory time, and inspiratory to expiratory ratio must be coordinated to fit into the breath cycle. These are linked parameters in mechanical ventilation and are adjustable to address the patient's clinical pathophysiology, facilitate ventilator synchrony, and ensure patient comfort. Here's an example of the connection between frequency, inspiratory time, and the inspiratory to expiratory ratio. In this patient, the respiratory rate is set to 15 breaths per minute with an inspiratory time of 1 second and an inspiratory to expiratory ratio of 1:3. With these settings, the patient gets the complete breath in 1 second and has 3 seconds to exhale the tidal volume of 400 milliliters during the breath cycle before the next breath is time triggered. If I lengthen the inspiratory time, in this case to 1.35 seconds, you can see that the inspiratory to expiratory ratio changes to 1:2, and the time available for exhalation shortens to about 2.5 seconds to compensate for the longer inspiratory time. Let's see what happens if we increase the frequency to 18 breaths per minute. It cut the time for expiration to 1.5 seconds. An inspiratory to expiratory ratio of 1 to 1.5 seconds will be uncomfortable, and the risk of breath stacking is always a worry. Shortening the inspiratory time to just over a second allows you to maintain a slightly more comfortable 1:2 inspiratory to expiratory ratio. In upcoming modules, I will show you how adjustments to the ventilator control settings discussed in this lesson are made for specific conditions. If you want to learn more about the Hamilton T1 or play with the ventilator controls, waveforms, and modes, consider downloading the free Hamilton VenTrainer application for mobile devices and personal computers.